In this video, hyperparameter tuning will be discussed, and I will go through an application which will show how spam classification can be done using a transfer learning BERT model. Transfer learning is a technique where a deep learning model trained on a large dataset is used to perform a similar task on another dataset. We call such a deep learning model pre-trained model. While talking about hyperparameters, hyperparameters are the parameters whose values control the learning process and determines the values of model parameters that a learning algorithm ends up learning. The prefix hyper suggests that they are top level parameters that control the learning process and the model parameters that result from it. Some examples like train test ratio, learning rate, choice of activation function, number of hidden layers, number of iterations, number of clusters, number of like the pooling size, batch size. These are the very common examples of the hyperparameters we can change, and that will affect our training model, the trained model, and maybe output. Let's start with the installations. First, we'll install the Hugging Face transformer library. This library lets everyone import the wide range of transformer based pre-trained models. Next, I will import the libraries, the required libraries like NumPy, Pandas, which I will be required to load the data, and transformers is also loaded. Next, the dataset is loaded, the spam data version 2.csv, which is loaded, and it is now into as a data frame. Next thing is the dataset consists two columns, label and text. The column text contains the message body, and the label is a binary variable where 1 means spam and 0 means the message is not spam. Now we will split the dataset into three sets: train, validation, and test. Here we can see that the dataset is split into three parts. Now we have to fine tune the model using the train set and the validation set, and make the predictions for using the test set. Next thing will be importing the BERT model and the BERT tokenizer. In the next section, I will find out the max sequence length, which is 25, which is around 25. So I have to predict it 25, and I have to pass it to the next cell. So I will be using this max length 25 as the padding length. To encode all those data sets we had, the train, test, and model, we will use this 25 as the padding length. The parameter pad to max length is also true here, and the max sequence length is set as the max length. Now we will be converting the integer sequences to tensors. Whatever we had, the input IDs, the attention mask, everything to the tensors. Inside the torch library, we have the torch.tensor, so we can use that and just convert it into tensor. Now the parameters like batch size. As we have to load this into the tensor, so we have to create some data loaders which will help us to pass those to train the model. So for train and validation, we have to define those data loaders here, so that we can reuse that in while we are training the model. Now here I will be freezing all the parameters of the BERT model we are using. These are the common layers and the activation functions that I will use. And here you can see I am using the BERT model. And here you can see I will be using a fully connected layer. And the activation function I am using is a ReLU, followed by a dropout layer. And finally there will be another connected layer on which we are applying softmax. So this will be the model architecture we are defining. This is the input dimension of this layer, which is 768. For the output, it is 512. It is another hyperparameter which can be changed into any other values like 256 or 128. The architecture can be passed through the model, and we can push the model to the GPU we have allocated. And now since that distribution of the classes in our dataset is imbalanced. With the help of complete class weights, now I can calculate the class weights here of our dataset. Now we can use these weights into PyTorch's loss function directly. Into this null loss, this loss function of the PyTorch, we can directly pass this weight into this and get the cross entropy. This will solve the class imbalance problem of whatever we had in our dataset. Now to fine-tune the BERT model, I have to have an optimizer. For this we are using the optimizer from Hugging Face only. So AdamW from the Hugging Face is being used here. And now the main thing, we have to set the learning rate. Here it is set it to 10 to the power minus 3. Now the main part is to train the model. So here is the function which we'll be using to train the model. The dataset will be loaded to E2 using the train underscore data loader. To calculate the loss, we are getting the predictions from the same ID and mask, and from there we can calculate the loss of from these predictions and the original levels it has. Now it was iterating the whole thing, so now it will calculate the total loss, adding the total loss from the items from all the batches, and then this step function will update the parameters to the next iteration. So finally it will return the average loss and the total predictions from this function. Same thing again, validation data loader will load the data and pass it to this evaluate function. So on an unseen data set, on the test data, we will evaluate our model we get, and finally we'll get the score of the evaluation. And this function will also return the average loss and the total predictions. Now everything is ready. Now it is the model is ready to be trained. So I will be set here 10 epochs to run the model, and the model's weight will be saved automatically. So running this cell, we start training the model, and epoch 1, 2, 3 to 10 will be running, and after the training the model weights will be saved into this save weights.pt. The final validation loss we have got is 0.131. It was going down, so we will not train this further. So now we will be testing our model. To get the prediction, I will pass the test sequence and that test mask to the model, and I will get the predicted score. To get the index of the largest number, we'll use argmax here, because last time the last layer was softmax of the model architecture. sklearn has this function classification report, which has this precision recall f1 score, and from that it will print from the test y and the predictions, it will print those. You can see the precision is good here, like the precision is giving 0.99 for class 0. For the class 1, the spam class, it is giving 0.88 precision, recall is 0.90, which is great, and f1 score we are getting around 98% for both of this. So on a very small dataset, it is actually performing well. This BERT model, which we have trained again using some parameter, like changing some parameters and hyperparameters. So the accuracy here is 97% is showing. So we can say the model is performing pretty good. Finally, the conclusion matrix can be calculated, in which we can also see that 710 is detected for 0 and 1030, which is a very good number. So finally we can conclude with this, and thank you.